Okay, so our next presenter is presenting under the name of Hakasays, and he will explain what that means. It's actually a Japanese term, and his Japanese is a lot better than mine. And so Hakasays is a builder and experimenter that's been studying fringe sciences his entire life. His interests and projects have spanned a wide array of fields, from electronics to computers to engineering and machining. His guiding doctrine is that of MacGyver and Robert Heinlein, that specialization is for insects. He's attended multiple ESTC conferences and gleaned many useful ideas and experiments from the presenters and attendees, especially from the technically focused presenters. His most recent work follows Eric Dollar's foray into seismic forecasting, Tesla coils, cosmic induction, and parametric variation. Build a Tesla coil the way Tesla built them is meant to serve as a crash course into a simple, practical Tesla coil design and construction. We'll be touching on some of the differences between modern Tesla coils and the coils that Tesla builds, and why the coils today look so different from the ones Tesla photographed in Colorado Springs. According to Wikipedia, a Tesla coil requires 2 or 3 coils, but most of the coils we're working with only have one. No primary, no secondary. Just a single extra coil is all that is needed to achieve even greater effects. Eric Dollar demonstrated this himself with his cosmic induction generator experiments at the 2021 conference. The coils we'll be working with are in fact quite similar with the plans that you'll find on the internet. You don't need high voltage transformers or expensive measuring equipment to build coils. With luck, you might even be able to find light a full fluorescent bulb from several feet away using only a couple watts. Through experimentation, we've also refined Eric Dollar's coil calculator formulas and compiled them together into a simple online calculator, so new builders can predict with great accuracy how their coils might perform even before they build them. Enjoy the crash course and buckle up. So help welcome Hakasays.
MacGyver. Oh, let's have some fun here. Test, 1, 2. You got that? Okay, cool. Howdy, morning everyone. Yeah, let's get started. How many people build stuff? Whether it's mechanical engineering, electrical, woodworking, electronics. I see most people up there, so that's good. The stuff is for you. How many people have worked with Tesla coils, high voltage, things like that? Ever make a primary, secondary, make the little sparks and light bulbs? About half, maybe a third. How many built Tesla coils that had only one coil with no primary, no secondary? 2, that's about right. Oh, 3, yeah. So, anyway, I guess let's get started. This is build a Tesla coil, the way Tesla built them. So, we're going to start back with the late 1900s Tesla Colorado Springs presentation, photographs that he took, and we're going to look at that, compare it to what the Tesla coils look today. So if we look, this is a Tesla coil photographed late 1800s in the Colorado Springs laboratory. If we notice in the center, there's a large extra coil that is approximately a 1-to-1 height to diameter ratio. And what's barely visible on the outside is actually the primary and secondary. So there's a secondary winding in the back of the room and a primary of only 2 turns. But I'm going to go back 1 second. So Tesla coil, by Wikipedia, says it's an electrical resonant transformer circuit designed by inventor Nikola Tesla in 1891. It is used to produce high voltage, low current, high frequency alternating current electricity. Tesla experimented with a number of different configurations consisting of 2 or sometimes 3 coupled resonant circuits. The last year we've been working with coils that are just 1 coil, no primary, no secondary. And it turns out that that field itself is deep enough that can consume many years of an experimenter's work. There's so many variables, it's very difficult to work with. So we covered that. This is another view from the side of the shop. It's still kind of hard to see, especially with the presentation, but along the entire outside of the room is the primary and secondary. Consists of, I think it was 10 to 20 turns of thick copper, and then the primary was only 2 turns of copper winding the room. Does that look like any of the Tesla coils that you see people build today on YouTube, on the internet? Not so much. What's the difference? Why does that look so different from what you see built today? Are they the same thing? So, here. Does that look very similar to what Tesla had built, or does it look different? So we'll notice the extra coil on here is missing. That one only has 2 coils. The primary on here was 2 turns of thick strap. Primary on there is closer to 10 turns. The secondary on here, which we'll call this the secondary for purposes, we'll say the high voltage coil is many hundreds of turns of copper wire, whereas this one is less than a couple hundred. And you'll notice that one's not sparking very good, and that one is. So it turns out, if you go back to that era, there were multiple inventors with different apparatus, but one of the ones that catches your eye, if you compare it to a modern Tesla coil, is from Paul Marie Odin in the 1890s, who generated the Odin oscillator. So if we compare a modern Tesla coil with an Odin oscillator, we'll notice that it has the same primary-secondary configuration. We'll notice that it has a spark gap in the middle. We'll notice that there's a high voltage capacitor. In the Odin setup, there's a pair. In the modern setup, there tends to be one. We'll notice there's a primary and a secondary. And in this case, it has a primary with a low impedance to ground. But it's structurally almost identical to what you would see in a modern Tesla coil. But this was from Paul Marie Odin, not from Nikola Tesla. So they're different apparatus, and they have different characteristics and effects. So this is the Tesla coil, the Colorado Springs replica from 2019 that was presented at the other Energy Science Conference. And we compare Tesla's original coil with what was presented there presented from Eric Dollard. So it's difficult to see in the schematics, but on the very top right was what Tesla's notebook schematic of what he was building. The primary is omitted, and what it is there's the secondary coil and the extra coil and the antenna or dielectric lead on the end. We compare that to the coil from Colorado Springs. It has an effectively identical configuration with the secondary and Tesla coil in series with each other. And we'll notice the extra coil in here had only something like 100 turns. That was something around 100 turns. Secondary, about 20, primary, about 2, primary, about 2. So it's much more close match to what was done over 100 years ago. Now, if we compare those two, we'll notice that they have different effects. So a modern Tesla coil tends to be very tall with wide width of 3 to 1 or more. A Tesla coil that we're doing here tends to be balanced around 1 to 1. And you can go higher or lower, it does about the same thing. A modern Tesla coil has hundreds or usually more than 1,000 turns on it, wound over PVC pipe. The ones we have use dozens of turns. Modern Tesla coil tends to be high resistance because it's a lot of thin wire. The coils we have are relatively low resistance. The coils they had tend to have very high inductance with almost no capacitance. The coils we have, because there's a split in the windings, the dielectric field is allowed to build up and expand into space. So what it turns out is these Tesla coils are balanced in that they have a dielectric and magnetic field that both cooperate with each other. And that's one of the reasons why they look so different. So because the balance is much better, a modern Tesla coil has a low Q factor. It tunes over a wide range, whereas the ones we have a very high Q factor. They're very tight tuning within several kilocycles. And it's tight enough that it turns out that moving your hand anywhere in the room, just if I'm moving some small distance away from this coil, it's enough to throw it off significantly, so that you have full effect or nothing, just moving your hand a foot away. As a result of that, the modern Tesla coils tend to be wideband. These Tesla coils tend to be narrowband. And same thing, the modern Tesla coils have a stable frequency because they're only dealing magnetically, whereas these are unpredictable and very difficult to measure, calculate, and tune because all of these conditions that are involved. What material you're using, the thickness and composition of the wire, the spacing between the turns, the height to diameter ratio, the length of the wire, all of these play into effect. And it turns into a very complicated system, but between Eric Dollard's notes and the work and help with Griffin, we managed to make an online calculator that simplifies it to the point that you can wind a coil within a few percent of predicted. So you're not quite shooting in the dark if you're trying to make one. And the difference between the modern and the Tesla coil is I happened to do this experiment the morning that video was presented, but one of the electrical-minded YouTubers had done a presentation making a Tesla coil, and he actually was nice enough to have the meter on there, 20 volts at 1 amp. And you can see he can just barely light a tiny compact fluorescent bulb at, let's say 6 inches. We'll give him a little credit. The one that I had done the same morning using the function generator, I had made it to just about 3 feet. Demo's 4 watts, but that was only because I didn't have equipment that could measure accurately below 5. So it turns out it's actually significantly less than 4 watts. And lighting a full fluorescent tube, not very bright, but it does light it to multiple feet away using basically no power. So it's extremely efficient compared to, obviously, those types of Tesla coils. So we're all builders, so we need to actually get started and figure out where we're going to go from here. So we need a target frequency, which more or less determines our wire length. Most people are going to be working in the ham radio band, so it's going to be 20 to 150 feet of wire. Material selection, we'll go over that. Physical construction, testing, tuning, and experimenting, what we can actually do with this. So wire length, this is the thing that we did, which is come up with an online calculator. So when you're designing a coil, whether it's Eric Dollard, Aaron Murakami, Griffin, all of these Tesla coils can be wound to relatively good accuracy using this online calculator. Plug in the height, the width, the frequency you want, and it spits out the ideal characteristics of, or it at least will get you something that will work. Not sure if it's the highest efficiency. We wound about a dozen coils to get the calculator accurate enough to within about 1 to 5%, which compared to Eric's notes turned out to be closer to 15%. So we beat him in that regard. Other ballpark, because of the velocity factor, instead of I think it's 243 divided by the length in feet, but 297 divided by frequency in megahertz equals the wire length in feet. We'll get you in the ballpark. Framing materials, the best we want to use is polyethylene. So UHMW is ultra high molecular weight polyethylene, HDPE, LDPE, Teflon, or polypropylene. These have the best electrical characteristics at high frequency RF currents. Polystyrene is also a possibility. It doesn't have great characteristics. It's styrofoam, but because it has such a low mass, you can get away with using that as a framing material. Unfortunately, all the hardware store materials, polycarbonate, acrylic, epoxies, PVC, and wood tend to have relatively poor characteristics. You want to minimize the use. If you're experimenting, you can still get away with a decent Tesla coil, but it may not have the ultra high Q characteristics. You can make these things out of garbage. You can actually you could grab a polyethylene bucket from Home Depot and wind a couple hundred feet of magnet wire on it, and you will have a Tesla coil. In fact, Steve McGreevy, has one of the best performing 160 meter coils that is literally just haphazardly wound around a big ass polyethylene barrel, a recycling barrel. And he has one of the best performing coils that we've seen so far. So, yeah. Framing materials for small coils like this, 3/16 inch to 1/4 inch thick tends to work pretty good. The size, 4 to 16 inch, anywhere in here is a good starting point. You don't have to wind something scale model Colorado Springs because it'll cost too much money and you don't know what you're working with yet. We barely know what we're working with yet. For materials, plastic sheet and plywood and stuff often comes in 12 or 24 inch segments. So if you're determining the size, that's usually a good factor to start from. And then white or clear plastics tend to work better because they don't have the extra materials that darken them up tend to be carbon that lowers the frequency and lowers the characteristics. So white is usually the best to go for. Framing material, this took some time to develop, but it's explaining basically the same thing. The dissipation factor is the dielectric loss tangent, which is the long way of saying how much is lost over time in a Tesla type system. If you want to take a picture or whatever. I have all this stuff printed out too if anyone needs to take pictures later or you don't have a good shot or whatever. But the same thing, HDPE, high density polyethylene, UHMW is just denser polyethylene. Teflon, polypropylene, if you can find it, maybe plastic injection. But same thing. You can use these materials, but they tend to have relatively poor characteristics. Wire selection, our goal for this is we want the lowest resistance practical. Ideally, we want 0 ohms, but then we got a cable that weighs 400 pounds and costs $20,000, so that's not going to work. A good starting point, though, is 20 gauge or thicker copper magnet wire. That's most of the stuff we've been working with. If you're trying to go better and do the Rolls-Royce coil, you can do silicone-coated wire, silver-coated Teflon wire that all have really good characteristics. Litz wire, which is the multi-strand copper wire, tends to have really good characteristics out of RF. And one of the things Dollard used back in the Borderlands videos was the outer sheath of coax cable, just the regular ham radio coax cable, the outer conductor, because it has a very large diameter, works really good for making coils. So let's actually go build one. There's multiple techniques. Dollard has his own. A lot of people have tweaked. The idea is you can't use PVC pipe because if you wind it on PVC pipe, the dielectricity gets eaten up by the pipe and doesn't give you the magic characteristics. We want something that is minimal framing material and open frame, like all of the ones that you see here. I call this a jigsaw method because of the way it comes together. It's relatively simple construction. We don't need too much in the way of materials, drill bit, jigsaw, hand files. There's a few different ways you can do this. You don't need expensive materials, but they help. CNC mill for cutting wire grooves, a wood table to cut the discs and slots and things like that, but you can do it by hand. This was done by hand. General setup is you make a couple cylindrical discs and a set of risers, and then they join together in a jigsaw configuration like you see down here. We have our material, we cut out the disc, cut the top and bottom disc. This case I'm using a wood router with a circle cutting jig. If you don't have this, you can use a jigsaw. You can cut it by hand with a handsaw. It'll take a little longer, but it'll work. Next up, we need to cut some wire grooves. It'll be 6 to 8 wire grooves for a small coil like this, 10, 12, it doesn't matter. The width of the slots you're going to want to be the same as the thickness of the material. So 3/16 inch, 3/16, quarter inch, so on and so on. It doesn't have to be perfect. You can more or less eyeball it and it'll work. Next up, we cut the vertical risers and we put grooves into that. So it essentially jigsaw connects together. On the one side you would put that, and then when you flip it over you actually have to cut the wire grooves. You don't have to, but if you want to get a very consistent spacing like we have on these, it comes in handy. CNC machine is really nice, but you can do it with a handsaw file, things like that, to cut the wire grooves at a specific distance apart. And once you have that, you have them all cut together. Assemble it and wind the wire around it. Usually use a little starter hole to keep the magnet wire from slipping. Doesn't have to be perfect, maybe an hour or two really carefully, and not a whole lot of work, and by the time you're done you have a Tesla coil. And I'm using Tesla coil in the simplest sense. There's many ways you can wind them. There's many coils that you can make, but what I'm focusing on is on the simplest single wire, single mode coil, because there's years of experimentation in that. We don't have to do the 2 coils and the 3 coils and all the complex vector analysis stuff just to get started. We have to have a good framework to build from. And so you're done. You've built a Tesla coil. And these are some of the ones that we use to help refine the calculator, testing different height-to-height diameter ratios, different material selection, etc. So now we've got that done. We've made our Tesla coil sitting right here. So we need to tune it, and we need to figure out what we can actually do with it. What kind of experiments can we perform? So this is where it actually gets kind of cool. So what I have here is, as seen on there, a single Tesla coil. It has 1 wire on the top, 1 wire on the bottom. There's no top load bottom. It's very, very simple. The wire leads to the positive lead, which if we trace it down, goes to this little power meter, which goes straight into this function generator here. Function generator is very low power. And then to pick up the signal and help tune it, we have an oscilloscope and a probe, little short piece of wire. None of this matters. And I'm just going to let it sit, somewhere near the coil, and it'll be fine, and we'll be able to pick up, and we can actually tune the coil with this. Tesla coil in the ham radio sense is considered a quarter wave antenna if you're going with the deep math and stuff. I have to short circuit a few steps to try to get all this material done. But so we turn on the function generator, and we can see we're already pretty close. If I flip the frequency around, I'm at just over 1 megahertz, 1.006. If I tune the frequency up, you can see it comes up and down, and that's the oscilloscope probe picking up the dielectric field that's expanding into space here. So not only is there a magnetic field that's running through that, but because there's a spacing between the wires, there is a dielectric field that is built up from here. So the coil is resonant in the dielectric field. The spacing allows it to expand out into space. So essentially the whole region around here is part of the circuit. So if you'll notice, I can tune this up here to a high amplitude, and then just moving your hand even a pretty good distance away, you'll see how far I'm detuning the coil. That's changing the frequency by tens of kilocycles. And what else can we do with that? If we look at the power on here, the scope is set to 5 volt per division, so what are we? We're probably about 50 volts right here. The function generator is putting out 20 volts, less than 1 watt. And you can get an idea of how far the dielectric field is expanding into space based on the voltages out of here. I could actually turn it down a little bit more. 10 volts per division, we get a little bit closer. It's going to detune it because it's part of the circuit. But it gives you an idea of how much power we're working with. And then if this works right, I don't know if you can see it. It's not very bright. Let me tune this a little bit better. We want to maximize the wave here. So let's try, sorry, 1 second here. And yeah, I think you can see that. How much power are we using for this function generator? So this is a RF power meter, power SWR meter. And what we're reading on here, forward power, 0.29 watts. This is less than 1 watt. And as you see, it's essentially no circuit. We're just feeding the function generator straight into the bottom end of the coil. And you can see how far this is extending into space. So it's really tricky to balance this out. You can see how far we're getting. We're over a foot, about 1.5 feet. It's getting a little dimmer. Oh, went out. So that gives you an idea of what kind of coil we're working with here. So we're lighting a bulb more than a foot away with less than 1 watt of power, less than 1/3 of a watt of power, 0.27 watts. And I think a lot of electrical engineers, it might blow their mind because this shouldn't happen. You shouldn't be getting over 1,000 volts off of the end of this coil and lighting a bulb at, I don't know what this bulb is rated. What is it, 20 watts or something like that? It's not full brightness, but it's actually lighting. All of the energy is going into space, getting picked up by this. And if my friend here doesn't mind, we can actually do measurements and see how far that field is extending into space. So the way I'm tuning here is using an oscilloscope, but you can actually use multiple different techniques here. Yeah. So one of the ways that you can do this is with a field meter, which is basically a small meter and a diode, so it's rectifying the current. But you can see what Griffin's doing here. He has the coil in free space, and you can actually see the needle deflecting by the electrostatic field that is filling the room with this, with 0.27 watt function generator. And how far does that actually go back if you put it on full sensitivity? Yeah, so you can see it deflecting. That's about 5, 6, 10 feet. Yeah. So this Tesla coil is, because of the electrostatic field, is resonating, and everything within that field is part of the circuit. the air is acting as part of the capacitor. And that's how we were able to get such incredible efficiencies, lighting bulbs at multiple feet with nothing. At my shop, the best record I have with this was 3 feet, barely lit with the bulb, and this exact setup here. Turns out this is one of the best performing coils that I have. That covers the simple. You can actually use probably, if you're really poor, you could probably use a neon bulb. There's different ways to do that too. There's one more demo that I had for the small scale. So this was the 1/4 watt. There's actually a system that's a little bit smaller than that. I forget the name of it, but this is a LTC something. It's just a little 5-volt frequency generator. And I'm running it off of a little USB power supply. It turns out it uses so little power, you can't get the power supply to stay on, so I actually have to charge my phone while I'm powering this. But this won't generate quite the same feel. If I hook that up to the same Tesla coil, we'll have to tune it a little bit. Not nearly as much power, but enough to get a volt at a decent distance. It gives you an idea of the field that we're working with. This is only 200 volts per division, so a watt or two sitting over here, or a volt or two sitting over there. But if we look at the USB power meter, it's put, this little circuit is drawing 5.13 volts at 0.000 amps. So it's below the measuring capacity of the USB thing. And over a volt, if we go further back, what do we got? We're probably in the, what is that, 1 volt per division, so that's about 6 or 10, 20 volts at this distance. It's not generating free energy, anything magic like that, but this is a transformer. This is transforming 5 volts into hundreds and hundreds of volts, and like I said, no primary, no secondary. This is a transformer by itself. So that's why I'm calling it a Tesla coil, because it is a high voltage magnifying transformer. We can go more and more complicated. We can have dual coil arrangements that are opposed. We can have the Colorado Springs setup that uses 3, but this is complicated enough just to get started. There's one more demo that we have here. I'm not sure if it'll work quite right, but so one of the other experiments that I did at the shop before coming to here was essentially we end up with a pair of Tesla coils in the what Eric Dollar calls the cosmic induction generator. And what ends up happening is the electrostatic field and the fields that are generated by this compound against each other. They smash into each other, and for their setups, they light up the bulb in the middle and generate all these interesting effects. But one of the interesting things with that is it's the power that you can pump into that is interesting because you can put many hundreds of watts into this, and it doesn't generate heat in the way that you would normally expect. So this isn't exactly the setup, but I have a similar coil. We couldn't quite tune it up, but the idea is this is a high voltage ham radio amplifier supply rack that lets me get something like 1.6 megacycles to, it's all the ham radio band, 1 to 30 megahertz or so at theoretically 2.5 kilowatts. So it has enough juice to work with it. But it turns out that Tesla coils, because they have such a tight tuning, they're not designed for ham radio, apparently. You're not supposed to run Tesla coils with a ham radio. So I had to make some modifications to the transmitter to get it to work properly. But even with that, the tuner can be a bit of a pain because, you move your hand 2 feet away, and at a kilowatt, you throw the frequency off, throws the SWR off, thing trips itself out, and, you're back to square one. But to paraphrase, I was using this at the shop in a very similar configuration with a cosmic induction, the dual opposed Tesla coils in the same configuration. And what you end up doing is you pump power into each end. It collapses in the middle. It combines. And the amount of power that you put in there, the energy appears to the energy seems to disappear. So what I was doing in my experiment was it was about 800 to 1,000 watts continuous into this pair of coils for, it was something like 2 to 5 minutes. So what's 1,000 watts over a few minutes? In a normal setup, you would expect it to generate tons and tons of heat. but once I turned it off, you feel it. It was warm, 100, 110 degrees, warm to the touch, but you could touch it. So there was almost 1,000 watts leaving this transmitter, going into that pair of coils and disappearing. It wasn't generating substantial RF power because you can't detect the field very far off into the distance. They basically cancel. So there wasn't a lot of RF power being generated. There wasn't a lot of heat being generated. There wasn't much of a field outside, so what happened to the energy? I don't know. That's for you guys to figure out. But I do have this set up. The test that I did after that to sort of prove the effect was I took another, something with a similar impedance, some resistance wire, that was something like 30 ohm, close as I could get to 50 ohm, to get the same match to the coil that I had. And once I started powering it up, we'll see if this handles today, but what I'm going to do is I'm going to see how much power we can dump into this and see how much heat is generated with the equivalent amount of power. So I'm not sure what's going to smoke first, so we'll find out. So we're only 30 watts right now. It's nothing. It's just, kissing the top of it. We push it up 70 watts, 100 watts, 200, 300, 400, 500. Yeah, I'm going to let it sit at, let's just say 700 watts. So we let that sit for a minute. So you probably use a microwave. You figure out how much microwave might be 800 watts. So you figure out how long it takes to heat up a mug of water to boiling. You use a toaster. What is it, about 1,000 watts? You figure how long it takes to burn the piece of toast. Oh, yeah, it is working. Okay, so there's enough heat being generated by the resistance wire. You can see the paper start to singe from the power that's being dissipated. So this is the same setup that was going into the pair of Tesla coils that wasn't generating that kind of heat. That it was safe to the touch several minutes later at almost twice the power that it was before. So here we're at 750 watts. It is going to change because the heat's going to change the resistance. But that gives you an idea of how a power dissipates in a normal setup, in a normal wire setup. So we haven't done energy synthesis by parametric variation of impedance or any of the magic stuff, but we did manage to destroy several hundred watts of energy into something. And the premise is that if you can destroy it into something theoretically, or we'll say conceivably, you might be able to get something from the same source. It means there's an interaction. There's something that's breaking the rules in a way that we don't quite understand. And I think really there was a couple more things on here. Top loads, when you're building your own coils, the top loads drag down the frequency, not too important here. Some of the other experiments we can do besides this, we can do single wire lighting. You touch a fluorescent tube and you can turn that into a tube driver that's extremely high efficiency. Wireless lighting, as you can see, separate the tube and you can actually light it at some distance away. We can study the monopolar field properties because a Tesla coil, there's a bit of magic here. It's not acting like a normal coil, and it warrants deeper study to figure out what's actually going on. So you can see, measure what's the magnetic field at different sections, what's the electrostatic field. Vector network analyzer would be very nice to figure out what's happening at different parts of the circuit. Low band ham radio antenna. This is a roughly 1 megacycle coil, so this is right in the AM band. One of the other ones that's about that size on the corner there is somewhere around the 160 meter ham radio band, which I don't know if anybody has seen, but 160 meter band is usually something that farmers use because it needs 100, 200, 300 feet of wire to get an antenna. And instead of needing the 300-foot antenna, by winding it on the coil, we're able to sort of cheat and work the really low ham radio bands with very little or almost no antenna. Telluric, or ground signal power transmission. If you connect this to a ground and you drive the Tesla coil that way, you end up turning the ground into your antenna. Unfortunately, there's no way of cheating. So in a normal ham radio, you need a really big antenna to get a long way. In the Tesla mode, you need a really good ground. So instead of being 100 feet in the air, you're going to have to drive a ground rod or something, drive 20, 50 ground rods and get a ground impedance less than 1 or something in the water table. Maybe you toss a wire into the ocean or something like that to get the lowest possible resistance and drive one of these. But if you do it right, you should be able to get long-range propagation through the ground. Between the few of us that have been experimenting with this, we have had some successes at, what is it, 20 feet? Well, we're over 100 miles apart. We had some successful or potentially successful tests getting 145 miles at less than 100 watts, and it was no antenna. This is the antenna, and they just really good grounds on both sides, and we did have really intermittent but functional communication. But we're just scratching the surface, so anybody here can do the same type of thing and report back on the results. Time of flight experiments, this is one of my to-do list, but the hypothesis based on Eric Dollard, Nikola Tesla, and I believe Wheatstone, the prediction was that the propagation through the ground was supposed to have different characteristics than normal air transverse mode. And the hypothesis was that you get propagation speed that is pi over 2 times the speed of light, or 1.53 times the speed of light, which not incredible, but it is break the current rules. So I have a setup. Hopefully we'll get it in the next year to be able to confirm that and measure the exact propagation speed through the ground using a pair of coils at some distance. Parametric variation, that's when you're starting adding complexity on complexity. I'm not even going to touch on here because there's so much involved. But the coil has different characteristics, whether it's being sparked, whether it's being driven from the center or one end, when you're using multiple coils that are compounding, aiding. I'll just say it's a very complex field that warrants further study. And we're I think, what you would call the experts, and we're barely knowing what we're doing here. That's one of the reasons I'm talking here, is so that more people are building this and experimenting and help get more data and more rigorous experiments that we can see help guide us in where is the most important to look. Cosmic induction generator, this is what Aaron's presented, what Griffin's presented, what I've presented on my site, the whole thing of lighting bulbs between the pair of Tesla coils. And of course, we have a Tesla coil. We can also use it to make cool sparks. So it's more efficient, or significantly more efficient, as you can see here. So if you manage to wind a Tesla coil in the Tesla configuration, you'll get much better performance for the same amount of power. Commercial applications, we could have a dead simple one coil power supply. If we scaled this down, we could end up making a high voltage power supply that had only one coil. No primary, no secondary. It would take the output, rectify it, rectify both potentials, and have that charge a capacitor, and there's your high voltage source. So maybe possibly vacuum tube power supply or some high voltage experiments. Homemade theremin or anything like that, because as you notice, you're changing the properties of the circuit, moving your hand anywhere in there. You could also make a motion sensor that was impossible to break, because the dielectric field, there's no way around it. So you could have a motion sensor that was not possible to crack. Antennaless ham radio, same thing. The shorter you work on this, when you do this properly, your antenna disappears completely. So instead of having an antenna, you have a beer can or a dielectric top load or something, but you can run it indoors. As long as you're going through a good ground, you'll get a communication. Through the ground communications and power transmission, that's becomes much more complicated and probably requires the VNA to do properly. Luckily, there's a speaker coming up on that later that'll help give a little more detail. And if the longitudinal time of flight ends up being pi over 2 times the speed of light, we might end up being able to use it for commercial applications as a slightly faster than light communications array. Maybe stock traders would like it, I don't know. The only stuff I've demonstrated on here is the extremely low power stuff. As you saw, 0.27 watts lighting fluorescent bulb, but we're going to want more power because everyone wants more power. The way I did it was with conventional ham radio with the Mars mod, basically an all-band ham radio mod, so it works on all frequencies. I don't have to wind a coil to exactly whatever specs. I do recommend, if you are experimenting with this, especially at the higher powers, that you do have the ham radio license and you aware of the FCC guidelines. The general rule is don't mess with other people. When you're working inside with something that's predominantly electrostatic, you're not going to generate interference more than quarter, half mile. But when you're working telluric transmissions, when you're doing anything with an antenna over the function generator scale, you should have a good idea what you're dealing with. Back to this, HF linear amp. There's two different ways to do this basically. Driven, which is driven like from a ham radio, and free oscillating, which they would call Armstrong oscillator, or there's different methods that you can get it to ring against its own power. Solid state Tesla coils tend to use this principle. HF linear amplifier, this is a vacuum tube amplifier, but you could use solid state. I don't know if I'd recommend it because the high voltage feedback makes it a lot easier to let out the magic smoke, and I've spent enough money with solid state ham radio amplifiers to not recommend it. ZVS is a zero voltage switch. SSTC, solid state Tesla coil drivers, those are effectively the same circuit. You can use that to drive a primary to end up working with Tesla coils in this regard. That'll put you up to a couple kilowatts, and that's probably the one where you're going to be making sparks with. Armstrong oscillator, that's what Adrian has over here. That's also what a lot of you'll see online if you look up vacuum tube Tesla coil. The schematics and guidelines they give you is generally an Armstrong oscillator setup. Didn't have enough space or room or weight to bring everything, but that was one of the ones I was interested in. Vacuum tube, very simple once you see the schematic and actually start building it. A year ago, I had not touched a vacuum tube, but thanks to Griffin and some research online, I'm pretty comfortable making vacuum tube coils that function, well, decently. Neon sign transformer will work too, and I think that is it. So all I say to finish this is go forth and build. I hope I've given everybody enough information they have to begin constructing, experimenting, and messing with this stuff. How do we say? It's the only reason I'm up here. I wasn't planning on doing a presentation or anything like that, but the problem was there's only about 10 people that are alive that I'm aware of that could actually talk about this and show something relatively simple. So I sort of had to do it. So I hope what I've given gives people enough information to get started, start experimenting. If you do end up winding your own coils, please message me, send emails, pictures of all the diagrams, the size, every spec that you can of the coil and how it performs, because everything that you give us, we can use to help refine the online calculator. So the better that gets, the better understanding we get. Everything's going to work forward from here. That's my info, and yeah, hope you guys have enough to work with. Thanks.
Awesome. If you have questions, step on up to the mic for questions.
No questions is either going to be a really good or bad thing. Hakasays is a bilingual play on words. Hakasay is a Japanese word for professor or scientist or teacher. So Hakasays is professor speaks. And yeah, I find it's fitting.
Okay. Thank you very much.